Welcome to Lecture 1 for Chemistry 312, Radiochemistry. This lecture provides an introduction to the course. The readings for Lecture 1 include the chart of the nuclides. There's an electronic and a hard copy that's available. The how to obtain the hard copy is described on the Canvas site. We'll also have the table of the isotopes, and then the lecture will be supplemented by readings from Modern Nuclear Chemistry, Chapter 1. The links are at the home page on Canvas for these textbooks. Lecture 1 is divided into two parts. The first part goes up to the discovery of the actinides, and the second part focuses on radiochemistry terms. The first part, which is this lecture, covers the class organization, which will discuss outcomes and gradings, and then a history of radiation research. Lecture 2 will cover chart of the nuclides and table of the isotopes, and an introduction to the terms that are often used in radiochemistry. The intent of this course is to increase the potential pool of researchers in radiochemistry. The fields of radiochemistry include nuclear fuel, radiochemical separations, development of nuclear waste forms, nuclear forensics and the nuclear fuel cycle, safeguards, nuclear reactors, and radiopharmaceuticals. There are other areas including environmental radiochemistry and fundamental research, which we're going to discuss and fall into all these other areas. The goal of this course is really interest students in radiochemistry and provide a route to radiochemistry research. At UNLV, there's ample opportunity for students to get involved with the UNLV radiochemistry program, and we use this course as a potential pool of students to engage in research both at the undergraduate and graduate level. And if you have an interest in performing research in the UNLV radiochemistry program, please contact myself or any other professor in the UNLV radiochemistry program, and we'd be happy to see what we can do to get you involved in our ongoing research. The course includes the physics of radioactive decay and the chemistry of isotopes. Fundamentally, radiochemistry is at the intersection of the periodic table and the chart of the nuclides. The periodic table has structure, as chemists, that one understands, that are based upon the electrons, whereas the chart of the nuclides has structures and describes properties that are based upon how the nucleons, the neutrons and protons, are engaged in the nucleus. So periodic table, electrons, chart of the nuclides, neutrons, and protons within the nucleus. And within radiochemistry, we want to emphasize elements with only radioactive isotopes, since they're unusual examples. So as examples, technetium, element 43, sits in the middle of the periodic table. We'll discuss the chemistry of technetium, and we'll particularly focus on the chemistry of the actinide elements, which are those elements that have 5f electrons that are at the bottom of the periodic table. The course topics includes the chart of the nuclides, details on alpha decay, beta decay, gamma decay, and fission. You should understand what the differences are in those by the end of the course. Methods and data that are obtained from investigating nuclear properties. We'll have discussions on the fundamental chemical properties that are involved in radiation radiochemistry, and particularly how they intersect with the elements that are only available in radioactive isotopes, such as technetium and particularly the actinides. We'll discuss how isotopes are produced, and we'll talk about how radiochemistry is used in research and technology. The textbooks that will be used in this course are primarily PDFs, and they'll all be linked to the Canvas website. The two textbooks that we'll use include Nuclear and Radiochemistry and Modern Nuclear Chemistry. And one thing that I want to note is that input from students are valued for this course. Participation is expected, and any sort of assistance with course development is valued. And the output obtained from the students should enhance the online course experience. The course has 7 outcomes where at the end of the quarter, the student should have some expertise, experience, knowledge in a few different topics related to radiochemistry. First outcome is understand, utilize, and apply the chart of the nuclides, the table of the isotopes, to radiochemistry and nuclear technology. Primarily, this is understanding how to obtain the data that are presented in those documents and utilize that information. Another thing the students should understand is the structure of the nucleus. Often in chemistry, we ignore the nucleus, but within this course, we do want to investigate the fact that the nucleus has structure. Here there's an example of the oblate, spherical, and prolate nuclei, and we will discuss within the course how this structure is understood and what's the relationship between the shape of the nucleus and some behaviors that are observed. Another aspect of radiochemistry that should be understood is the chemical properties of radioelements. Those elements that are only found as radioactive isotopes. They include the actinides, which are filling 5f electrons, and then technetium and promethium, which are elements that are normally found in the stable region, those elements below 83 protons, but are in fact radioactive. The students should also be able to comprehend and evaluate nuclear reactions and how isotopes are produced. This can be obtained and understood from using the chart of the nuclides. One can evaluate certain reactions. So for instance, here's a reaction shown here of a proton and nitrogen 15 makes oxygen 16. There's an alpha particle decay that makes carbon 12. That's in an excited state. It gives off a photon. Now it makes a ground state, carbon 12. The course will describe not only understanding how the particles and the isotopes react together, but the probabilities of those reactions. And that'll include cross-section data, understand what are some of the reaction particles. So for instance, an alpha particle, how that can be a product or can also be involved in a reaction. And then energies in the reactions. Where do these energies come from? Well, a lot of it comes from conversion of the mass from the starting compounds to the product. And we should also explore and understand the different types of radioactive decay. And by evaluating the chart of the nuclides, understand the location of the isotopes and what's the probability of a certain decay coming from those isotopes. For instance, heavier isotopes tend to decay by alpha. Those isotopes that are proton rich tend to decay by positron or electron capture. Those that are neutron rich tend to decay by beta minus. And then we'll discuss relationships between half-life and decays. The course will also describe how radiochemistry can be used in research, how, as an example, concentrations, very minute concentrations, down to femtomolar per liter or even less, of isotopes can be measured. My thesis work, I studied one atom at a time chemistry, so one can do incredibly small concentrations, and how we'll describe how these concentrations can be evaluated and how isotopes, making radioactive isotopes of normally stable isotopes, can be used to expand our understanding of systems. And finally, the course will investigate modern topics in nuclear and radiochemistry. This will be brought in the lectures, in discussions, and then in the final, we'll have presentations, papers, and employment opportunities, which will hopefully link together what was learned in the course where radiochemistry is going today. Information on course grading, which may interest some of you, is presented here. At the end of each lecture, there is a PDF quiz. Those PDF quizzes are in total 15% of your grade. They're based upon the presented information, and the preferred submission is on the Canvas site. However, you can also send them as attachments to email. There are 4 comprehensive quizzes, each 15%, that are based upon the topics covered in the lecture and the PDF quizzes. At the end of each lecture, there's examples of questions. Those would be the good basis of study for the quizzes. These quizzes are take-homes with the due dates provided in the within the quiz. You have 5 days to complete the exam. The answers are posted after the 5th day. And then there's a second submission where any corrections will have 50% of the grade. and there's 3 days to make this second submission. The goal of the quiz is to demonstrate the comprehension of the material. So for me, the ideal quiz, everyone gets all the information correct, and I can see that everyone understands the material. The final is comprehensive. It'll include a paper, a review of a presentation, not a presentation that you'll give, but a review of a presentation online, and review of positions in radiochemistry. You'll basically read them and discuss what the course information is provided for your understanding of the information on the paper, the presentation, or the position review. And then class participations, 10%. That's blogs, office hours. Responding to the blog is a key way of getting 10% extra points. The outline for the course is presented here with the topic, the date that it's online, the date that it's due, and the number of presentations for the given topic. The due date doesn't change. However, the date that the lectures are presented may change. The lectures may be presented earlier. If they're presented earlier, the due date won't change. You'll have more time to do the work. The exam dates are also listed here. As you see, we have the date online, the initial due date, and the second due date. For the exam periods, we will have, during this time between the date in which is posted and the due date, we will have office hours in which questions on the exams will be discussed. The final exam will be posted on the first day of the final exam week and will be due on the last day of the final exam week. All right, let's start discussing some radiochemistry information. We'll talk about the history of radiochemistry development, how it's linked with really the nuclear science development. You see how they're together and how they played off each other and some of the roles radiochemistry played in how we understand physics today. So a little over 100 years ago, in 1896, Becquerel discovered radioactivity. Becquerel had this salt, this potassium uranyl sulfate, and he exposed it to sunlight, and he wrapped it in photographic plates, and he put that in black paper. So the photographic plate at the time, if you think about it, it's still kind of early material back in the late 1800s. The plate, when they were developed, they showed this image of the uranium crystals. And what Becquerel actually thought is that the sunlight absorbed light and that this uranium salt fluoresced and gave off that light. That's what he proposed. And for this, for this proposal, the discovery of radioactivity, he was wrong, but he also won a Nobel Prize for that. And then just a few years later, radium and polonium were isolated by the Curies, who are shown here. Marie Curie, possibly the most famous radiochemist, and her husband Pierre Curie, who also was a Nobel laureate at the time. So Marie obviously went on to win 2 Nobel Prizes, if you remember from your history. Right about the turn of the century, in 1899, Ernest Rutherford identified the alpha particle. The radiation was divided into alpha, beta, and gamma components, and it was based upon the ability of these different radiations to penetrate objects. So alpha penetrated an object the least, beta a little bit more, gamma the most. So alphas could be stopped with a piece of, small piece of paper, beta an aluminum foil, and gammas very difficult to stop. 1909, the alpha particle was shown by Rutherford to be the helium nucleus. He determined the charge to mass ratio, so this alpha particle gaining more information. 1911, the Rutherford atomic model. Thomson had a plum pudding model that was negated by Rutherford. They demonstrated some high central charge, a small volume, and this was demonstrated by an alpha particle scattering on a gold foil. It's from this scattering, the hypothesis was developed that, well, the mass must be all concentrated in an area where the particle would impinge upon this nucleus and get scattered back. Detection of alpha particles and detection of other particles was expanded upon in 1912 by the development of the cloud chamber, and then a planetary atomic model was postulated by Bohr back in 1913. So after the discovery or the postulation of the Bohr model, where the electron orbitals are a little bit better defined than Rutherford's model, 1914, the nuclear charge was determined by X-rays. This was postulated and demonstrated by Moseley, who was working again at Rutherford's lab. 1914, and then you see a gap between 1914 and 1919. The first war stopped a lot of, obviously a lot of research. And in fact, Moseley, who was working in Rutherford's lab, could have avoided the war, but wound up getting killed in France, and really was identified as one of the greatest losses of science due to a military conflict. 1919, artificial transmutation by nuclear reactions was observed. Again, Rutherford. He bombarded nitrogen-14 with an alpha particle to make oxygen-17. Well, nitrogen-14 got from the atmosphere, and the alpha particle was from a radioactive source. He just identified that you could have this nuclear reaction occur. Again, so you can see that Rutherford's lab was putting out a lot of great research, great researchers. 1919, mass spectrometer, first development. 1928, the theory of alpha radioactivity by Gamow, which utilized the concept of tunneling through a barrier to describe the decay. 1930, Enrico Fermi proposed the neutrino hypothesis, where there's a massless particle with a spin of 1/2 that was used to explain beta decay. When we discuss beta decay, you'll see the importance of Fermi within understanding beta decay. 1932, the first cyclotron, which is shown here, which you could hold in your hand, was made by Ernest Lawrence at UC Berkeley. As a graduate of the UC Berkeley radiochemistry program, there's a plaque at the chemistry building on campus at UC Berkeley that describes the radiation lab where these experiments were performed. In 1932, the neutron was discovered by Chadwick, and he used some data, some scattering data to calculate the mass. This led to a proton-neutron nuclear model. Again, this is all at the Cavendish Laboratory. 1934, discovery of artificial radioactivity, the Jolets and the Curies. Again, the child of Pierre Marie Curie, getting involved in the same sort of research. 1938, nuclear fission was discovered. Hahn, Meitner, and Strassmann. So Lisa Meitner, Otto Hahn, Fritz Strassmann discovered nuclear fission, 1938 in Germany. This was actually, from people that I'd worked with who were on the Manhattan Project, this was actually a very important consideration, that the Germans had this understanding of fission, that they were fundamentally technically advanced in this area prior to the Second World War. But in 1942, Enrico Fermi and others made the first fission reactor at the University of Chicago. It's called the Chicago Pile. 1945 was a Trinity test, where first plutonium and then eventually a uranium device, not a Trinity, was tested. And then 1947, radiocarbon dating was explored as a way of dating material. So within this period, the artificial radioactivity was a rather large advancement, showed that isotopes that are somewhat different could be formed. And here's an example of a painting from University of Chicago, the first reactor, where it's a air-cooled, graphite-moderated reactor. And then you see this students, the graduate students here, who would be called upon in case the reactor went out of control, where they could help release agents that would control the nuclear reaction. Here's the latest periodic table. I want to call your attention to the heavier elements. That you should notice that there are 118 named elements on the periodic table. Some of the more recent ones include flerovium, livermorium, tennessine, oganesson. The UNLV radiochemistry program, which I'm also a part of, was involved in the discovery of tennessine. As a graduate student, I was fortunate enough to work with Glenn Seaborg, who has an element named after him. And I also, when academician Flerov, who has element 114 named after him, with the Flerov Institute, visited UC Berkeley. His English wasn't very good. I speak some Russian, so I took him to San Francisco. We went to Chinatown, and I got to hang out with him. That was a very interesting time. Technetium, which is shown here, sits right in the middle of the periodic table, is a radio element, only available as radioactive isotopes. Promethium, another element that one would think should be stable, is not. Okay, and then elements above bismuth, so elements with proton numbers greater than 83 are all radioactive, so polonium, astatine, radon. All the actinides shown here, and then the transactinide elements. At the University of Washington, one should note that astatine, this element is produced. Astatine 211 is made at the cyclotron at the University of Washington, and it's used as a radiopharmaceutical. It's attached to a ligand, and the alpha is used to kill cancers. So let's start with the lightest radio element and its discovery. It's technetium. It was confirmed discovery back in 1936 at the University of Palermo in Sicily. Pierre and Segre, Emilio Segre, actually did the separation, but they obtained material from Ernest Lawrence, and he mailed them a molybdenum foil that was used as a cyclotron deflector. So that small cyclotron that Lawrence made had a deflector on it where particles would bombard. So that molybdenum, which is a Z of 42, was getting hit with alpha particles. There were nuclear reactions where the molybdenum was gaining a proton going to Z of 42 to 43, 43 being technetium. They separated, dissolved it, chemically isolated some other element that was separate, that was different in chemical behavior from the molybdenum, identified it as technetium-95, technetium-97, and they named it after the Greek word technics, meaning artificial, so technetium. The University of Palermo officials wanted to name it after the Latin name of Palermo. And then eventually, Segre and Glenn Seaborg worked together to isolate technetium-99M. The M means that it's a metastable state, so it's in an excited nuclear state. It's radioactive, and it decays by just emitting a photon. Goes to technetium-99, which is a long-lived radioactive isotope. And we'll learn that this technetium-99M is the workhorse for radiopharmaceuticals. About 80% of all radiopharmaceutical applications use technetium-99M, and that photon is used as an imaging agent. Promethium was first produced at the Oak Ridge National Laboratory in 1945 by primarily Coriell and others listed here. It was from a fission product. There was a lot of work going on in the understanding the reactions of fission, getting materials from the fission, including plutonium, separating out the lanthanides. It was known that there was a gap in the periodic table. Understood from this one could understand some of the expected properties of this promethium. It was separated and the analysis of fission products of uranium fuel irradiated in the graphite reactor at Oak Ridge showed the presence of this element. It was announced in 1947, 2 years after the discovery, and in 1963 they made about 10 grams of promethium from used nuclear fuel, so a large amount that one could do real chemical studies on. Then other synthetic elements, we'll start with neptunium. If you look at the actinides, you go from actinium, which there are trace natural actinium, thorium, which is naturally available, protactinium, which is part of the decay scheme of uranium, and then uranium, which is also naturally available in mined. So neptunium would be the next element that's synthetic, and it was the first synthetic transuranic element to be discovered, and it was the isotope neptunium-239 was produced by McMillan and Albertson at UC Berkeley in 1940. They bombarded uranium with cyclotron-produced neutrons. So these neutrons were produced by hitting a particle into a beam stop. So for instance, a piece of carbon, any sort of material, extra neutrons would come out. Those neutrons get absorbed by uranium-238. They would make uranium-239. That uranium-239 would beta decay to neptunium-239, which has a half-life of about 2.4 days. They isolated this small amount of neptunium from a large amount of uranium, showed that the chemical property was different than the uranium. However, the chemical properties of uranium, they weren't understood at this time in 1940. The actinide elements were part of the transition series. So uranium was grouped under tungsten. It wasn't until Glenn Seaborg later came up with the actinide hypothesis that moved the actinides where they currently live on the periodic table. But they showed that they showed some similar properties to uranium, but not completely. Eventually, macroscopic amounts of neptunium-237 were produced with a faster neutron on uranium-238. So a neutron would come in, it would knock out 2 neutrons, it would make this uranium-237. That would beta decay to uranium, from uranium-237 to neptunium-237. And they made 10 micrograms of material. They eventually made much more neptunium. Now one can get, certainly tons of, many multiple grams, kilogram quantities of neptunium-237. Plutonium synthesis was the second transuranic element of the actinides to be discovered. Plutonium-238 was produced in 1940 by Seaborg, McMillan, Kennedy, and Art Wall. Art Wall was the graduate student, so he really did the bulk of the work. And this was produced by using the 60-inch cyclotron at UC Berkeley. So the diameter of the cyclotron was 60 inches. The reaction was they took a target of uranium-238, hit it with deuterium. 2 neutrons came out. They made this neptunium-238. That neptunium-238 beta decayed to plutonium-238. The oxidation of the produced plutonium showed that it was different than the chemistry of the uranium. They identified the differences in the chemistry of the element. They were able to use radioactive decay to identify some of the properties, the alpha decay energy, get an idea of the half-life of this isotope. Eventually, in 1941, plutonium-239 was produced, where uranyl nitrate in a wax was behind a beryllium target that was bombarded with deuterium, so a lot of neutrons. The paraffin block would thermalize, would slow down those neutrons. So the uranium-238, in this case, would absorb a neutron, make uranium-239. That would decay to neptunium-239, and that would decay to plutonium-239. There was a separation with fluorides and extraction with diethyl ether, and they showed that, like uranium-235, neptunium-239 would undergo fission with slow neutrons. And for this work, Glenn Seaborg and others were awarded the Nobel Prize. The transplutonium element discovery, americium and curium, they were first produced in a reactor by neutron capture. plutonium-238 would be in the reactor, would gain a neutron, make plutonium-239. That would capture a neutron, make plutonium-240. Plutonium-240 has about a 15-year half-life. It would beta decay to americium-240, plutonium-241, beta decay to americium-241. Again, chemical differences in decay properties. This route could also keep, if you kept bombarding, not only would some of this plutonium-241 decay, some of it would also capture. And you could make up to curium-242. There are also routes for doing direct production. So plutonium-241 would be produced. It would beta decay to this americium-241. And the plutonium-241 was produced by the reaction of uranium-238 plus an alpha particle. And then you could get the another sort of direct production by using the same sort of reaction, except with the uranium, use neptunium-237. The way we would write a reaction for the production of curium-242 is shown here, where one took plutonium-239, bombard it with helium, a neutron would come out, and you would make this curium-240. The chemical separation from plutonium was achieved, and this decayed, the curium-242 decayed to plutonium-238. That was understood. They understood the energies and the half-life of plutonium-238. If they saw something decay to it, and they knew that that decayed in alpha, you actually had a genetic relationship. So you could clearly identify a produced isotope from something that had an alpha decay. They did show that they had difficulty separating americium and curium from the lanthanide fission products because they're all involved in, they all have the same trivalent oxidation state. And on the web page, there's an announcement on the discovery of these elements. The elements in order to be discovered next are berkelium and californium. One can guess where they were made. A trend that was established earlier, they required targets of americium and curium. So the new elements that were made were then used as targets. They had to get sufficient amount of the new elements. Then they would bombard these targets with an alpha particle. So you would go up to, you use americium to make berkelium. You use the curium to make californium. They separated these from the target material. So again, remember, this is +3 oxidation state. Berkelium actually has a +3/+4 oxidation state, +3/+3 oxidation state. One would do column chromatography. You could calibrate the chromatography system with some lanthanides. But what's shown here is the log of the activity versus the drops of the eluent. And you would see that there's different spikes of the activity. And the lighter, the lighter the element, the longer it takes it for it to elute. So the heavier elutes first. And this has to do with the change of the ionic radius. As the lanthanides get heavier, as the actinides get heavier, the ionic radius contracts. So if we use this method to investigate new elements, where would you expect the heavier actinides to elute? Well, anything that's heavier than californium should elute sooner. So that's actually a useful tool because these heavier elements are going to be made in less amounts and also tend to have shorter half-lives. So having them come off the column quicker is beneficial for their discoveries. So you can see where you would have these separations, the number of drops coming off a column would be sufficient to collect and identify the different elements. That's where the heavier elements you would expect them to elute. Einsteinium and fermium, well, we made a little change here. They were actually first produced in the thermonuclear test, the Mike test. You can see information about the Mike test on this YouTube video. There were also new isotopes of plutonium, plutonium-244 and plutonium-246. The thermonuclear test, a hydrogen bomb. You started off with uranium-238 and you made successive captures on the uranium-238. So you go from uranium-238 to uranium-246 in an instant, and then that uranium would beta decay to make different elements along those different isobars. There was an example here of the correlation between the log correlation of the yield versus the atomic mass. So this is an example of nuclear forensics where one was able to identify information about the yield of a test from the production of different isotopes. This was the first time there was production of trans-californium isotopes. So you would make these heavy uranium isotopes followed by beta decay. They made einsteinium and fermium. And as we will discuss in nuclear processes, this is similar to the R process that stars go through, the rapid process, and how elements are made. And as we described earlier, for americium curium, ion exchange was used to separate these elements. The final three actinides, the heaviest ones, mendelevium, nobelium, and lawrencium. These, with mendelevium, you wind up getting atom at a time discovery because the amount of target that you could make for these reactions with an alpha particle start becoming less. There's not a lot of einsteinium to start off with. You're not going to make a lot of mendelevium. The cross sections get smaller. So they're requiring a high degree of chemical separation. So what one would do is take the target, bombard it with helium nucleus, put a catcher foil behind the target so that the recoil nucleus would go onto this catcher foil, is usually gold. You would take that gold foil that had the recoiling product on it, dissolve it in acid, then do ion exchange chemistry. There was some controversy with nobelium. It was expected to have trivalent chemistry. It's actually divalent. If you look at how the electrons are filled, by the time you get up to nobelium, so element 102, you have a filled 5f orbital, so 14 5f electrons, and these two 7s electrons are open. So one could remove those two 7s electrons relatively easily. You have a divalent oxidation state, but trying to remove an electron from a filled f orbital is difficult. So nobelium had this divalent oxidation state. The first attempt cannot be reproduced. The final eventual reaction was shown here, where curium-246 was bombarded with carbon-12, 4 neutrons to make this 254 isotope of nobelium. There was an alpha decay of nobelium, and the daughter, the fermium, was identified by ion exchange. I was told by Glenn Seaborg that during this controversy, they knew that the Swedes who were doing the work wanted to name the element after Alfred Nobel. So as a joke, they called it nobelivium. Lawrencium was made from different isotopes of californium bombarded with boron, so stable boron, you get to 10 and 11. And then a new isotope was identified with a 6-second half-life as lawrencium-258. So one could see that there was this trend. We've obviously extended that trend to go all the way up to element 118. But the separations become more difficult, the half-lives become shorter, and the probability of the reaction goes down. Okay, this completes part 1 of lecture 1. You don't need to comment on the blog or respond to the PDF quiz yet, but please do so when you've completed the second part of this lecture.